Okay, I need you to turn in what you have, please. Okay. Anyone else? Last call? Last call. All right. That's it. All right. Well, shall we talk about it? All right. Let's before we talk about it, I sent an email out about, which one was it? Comparison test. So if you could get out your sheet, just make sure that on the comparison test, on part 3, where it says if the limit as n goes to infinity, a sub n over b sub n equals c greater than 0, it's supposed to say then both series converge or both diverge. C has to be finite. Okay, meaning that if you do the ratio test and get infinity, the test fails. So it has to be a limit, it has to go to a number, all right? So I sent that out in an email. I also sent out an email on Friday. I don't even remember what day it was. That I was considering when our next test was going to be, and it's on the schedule for this Thursday, but I don't know if, people weren't out there. Anyway, I sent that email out. I didn't get a whole lot of responses. The test is set for Thursday. It's going to cover everything up to what we finished today. That's what the people who did reply, that's what the majority wanted, and so that's what we're going to do. The advantage to it is that there's less material, and that you'll know Thursday night or Friday morning what your grade in the class is, what you basically need on the final to pass, and you can determine whether or not you want to drop the class, because this Friday is the last day to drop. Okay? So now to the quiz. You look at that, you start eliminating some possibilities here. It's not exactly geometric, but kind of geometric, right? Anybody try comparison? Try to compare it to something? Anyone do comparison? Yeah? Shall I try comparison or not? I don't care. How many of you did ratio? Okay. It'll work with ratio. Let me try comparison, see what happens. Comparison test says that if I look at this in here, I call that a sub n. And also be careful on the comparison test. Remember, your a sub n has to be bigger than 0, right? Which it is, right? That's always bigger than 0, all those. And I'd like to compare it to, I would assume, the geometric series. Is that 1 over 7 to the n? Okay, that's what I would have done if I was going to do comparison. Try and compare it to this geometric series. That's a geometric series with r's 1/7. It'll converge, right? When I add them up. So the question is, if my b sub n, if my sum here converges, then on my comparison, I need my a sub n to be less than or equal to my b sub n. Is that true, though? If I do n to the 4th over 7 to the n, is that less than or equal to 1 over 7 to the n? The answer is no, because this numerator is bigger than 1. The denominators match. So n to the 4th is bigger than 1, so that does not hold, and therefore this comparison won't work. Right? Limit comparison? Yes? So that would be, what would limit comparison be? Okay, same comparison or a different comparison? Okay, so I'm going to do the same. So I'm trying something different since that didn't work. You want to compare it to b sub n is 1 over 7 to the n again? And wait, ratio or limit comparison? Okay, so ratio test. Limit comparison test. Okay, you want limit So we're trying now the comparison, limit comparison. That's part 3. If I take limit n goes to infinity, my a sub n is still this. My b sub n is this. Then I should be putting n to the 4th over 7 to the n over what I'm comparing it to, 1 over 7 to the n. Why did I put limit equals? Sorry. Limit of this, which equals limit n goes to infinity. But these cancel, right? And so you get n to the 4th. And that goes to infinity. And this won't work. It has to be a finite c. So that doesn't work. So a lot of you did ratio. So let's just get to ratio test. Okay, ratio test. So for the ratio test, I'm going to take my n to the 4th, 7 to the n. I'm going to call that my a sub n, right? A sub n is equal to n to the 4th over 7 to the n. And I'm going to need to take the ratio of a sub n plus 1 over a sub n, absolute value. So here's the test. Limit n goes to infinity, absolute value a sub n plus 1 over a sub n, right? Which is limit n goes to infinity. What is a sub n plus 1? Plus 1 to the 4th over 7 to the n plus 1 times the reciprocal, 7 to the n over n to the 4th. If you did all your homework, you're comfortable now writing that step instead of writing the fraction. If you didn't do your homework, you're probably not used to that yet, but that's the flipping that takes place every time you do ratio test. And now what we're going to do is use the power property of exponents to rewrite a couple of things here. 7 to the n times 7 to the 1. 7 to the n and then n to the 4th. So all I did was broke up that bottom 7 to the n plus 1. And I get some good cancellation here. And what I'm left with is limit n goes to infinity of n plus 1 to the 4th over 7n to the 4th. Now, I got rid of the absolute value. I could have done it earlier, but I needed it at the beginning. The reason I got rid of it is because every term, every factor here is positive. So we don't ever have to worry about taking an absolute value at the end. Now, this gives you infinity over infinity, but you can apply L'Hopital's rule, right? Now, hopefully as a calculus student, you've gotten to the point where you know that when I take n plus 1 to the 4th and I expand it, that's n plus 1 times n plus 1 times n plus 1 times n plus 1, the first term I'm going to have is n to the 4th, right? Everything else is going to be a lower power. So when I do L'Hopital one time, right, power is going to come down. Do it again, it's going to come down. Do it again, it's going to come down. Eventually, it's just going to be the coefficient of n to the 4th on top over the coefficient of n to the 4th on, but you have to account for the 4 coming out and everything else, right? But is that okay? You don't have to expand it, is what I'm saying. It's okay. It just took a little more time. That's all. It's also helpful to know Pascal's triangle here, too. Because if you know Pascal's triangle, then the expansion's easy. But what you're going to get on top, right, when you... Do you want me to work it all out? I guess you do, right? If I were doing this, this is what I would have done. 4n plus 1 cubed over 28n cubed. I would have done derivative of top over derivative of bottom. I wouldn't have expanded it. Why would you? Yeah. Do you agree it's infinity over infinity, though?
Yeah.
The only reason is because if you expand it all, then eventually some of those terms go to 0. Right? Like the ones further down here that have lower degrees after like the second, third derivative of L'Hopital, they'll start going away. I would do, so that was L'Hopital. I'm going to do L'Hopital again. What do I get? 12, right? N plus 1 squared over, what's that, 60, 70, 84, N squared. That's still infinity over infinity. I go again. L'Hopital, limit, N goes to infinity. I get what, 24 N plus 1 over 168 N, right? And then I go one more time. If I do one more time, it's 24 over 168. And all I care is that's less than 1. After I take the limit, that's what I would get. Mm-hmm. Yeah, you could have done that. Yeah. I mean, there's different ways of doing it. I'm just, from here to this being less than 1, it can be done many different ways. That's just one way. Well, let's get to our conclusion yet. Okay. The ratio test says that if that limit of that ratio is less than 1, it converges, right? So therefore, our original problem, n to the 4th over 7 to the n, converges by ratio test. You could say absolutely converges also. All right, that was the quiz. Any questions on homework? 31? I did post the answers yesterday. I did post the solutions. I didn't realize they weren't up, and then I was told they weren't up, so I did them yesterday and then put them out there. So which one was this, 31? I didn't assign 31?
19 to 31. 19 to 31.
It's a tricky, little tricky.
We have to use root 30 and beyond. Well, 31 I got it. Doing ratio.
Let's see, arctan n.
Because n to the negative 1, n goes to infinity, pi over 2. Over infinity.
All right, here's the problem that I'm being asked about here. And so it's an alternating series, right? Alternating series, which means we could try alternating series test. What else could we do? We could try comparison, right? We could try the comparison because the bottom, n squared, is what type of series? 1 over n squared is p series, right? With p being 2, which means it converges. So what do you think? What do you think looks more promising? You think comparing it to a p-series might be better? Okay, if I'm going to compare it to a p-series, though, I need to look at the absolute value of this to get rid of that alternating negative 1, 1. So here's what I'm going to do. Consider this series instead. I'd like for us to take a look at the absolute value of this thing, right? So I'm looking at, instead of adding up all these terms of this sequence, I'm looking at adding up the absolute value of the terms. Yes? I definitely will need to understand what you're doing. Yeah. So I'm going to consider this as a completely different series, right? These aren't the same series. They're different. But remember that there's something that says here at the bottom of your page, it's the second to bottom one. It says that if the absolute value of a series or sequence, right, if the absolute value of the terms of the sequence converges, then the original one converges also. So if I can show that this one converges in red, then the black one has to converge. That's what I'm going for here. And the one in absolute value is really the same as just arctan n over n squared, because why? The negative 1 will basically be gone. Negative 1 won't make it alternate anymore. And both of those are positive. Is arctangent n positive? Not always, but for us it will be because of n. So if you need to look at what arctan looks like, we looked at it. I know we've looked at this already in class. The arctangent, I forgot about Pascal's triangle, sorry. Maybe later. This is what arctan looks like. Not tangent, arctangent. Is arctangent always positive? Yeah, from 0, past 0 it is. And remember, we're dealing with n's here. So I know the top's always positive, the bottom's always positive also. So I don't even need the absolute value anymore, do I? All right. Now, let's pick something to compare it to. And we said p series, 1 over n squared. Now, let b sub n be equal to 1 over n squared. This is p series p greater than 1, right? So I'll say it converges. Be careful, just be careful whenever you do something like this. I'm defining a sequence right now, right? B sub n. Don't say that that converges, because B sub n doesn't, we're not saying B sub n converges because it's a p series. We're saying the series, the sum of the B sub n's converge. So if you're going to say anything from this, you could say, therefore, the sum of B sub n's converge. But don't just say, oh, it's p series p greater than 1, therefore it converges. It means what? What converges? You see what I'm saying? The sequence, the sum of the sequence, the series converges, not the sequence. All right. With me? All right. Now, since we know that that's going to converge, the series of that p series is going to converge, we need the a sub n, which for us here would be this. We need that to be less than or equal to b sub n. So is it? Is arctangent, so I'm going to put here, I'm checking that a sub n is less than or equal to b sub n. So is arctangent n less than over n squared? Is that less than or equal to 1 over n squared? Yeah, what about arctangent there? Yeah, arctangent, right? Go back to the picture. How big does arctangent get? Pi over 2, doesn't it? Pi over 2, which is greater than 1. So this isn't going to work unless we modify it slightly. It'll be an easy modification. We could have done it earlier if we would have realized it earlier. See, the arctangent on top, the biggest it ever gets is what? I mean, the biggest it'll ever get is pi over 2, right? So the problem is my 1 is smaller than that always. So why don't we pick something other than 1? How about pi? Anything bigger than this, right? And it's a constant, so does that affect the p series? No. So come back up here to the b sub n and change the numerator to, let's say, pi. Then this pi down here Now, is that true? Is pi over n squared bigger than arctangent n over n squared? Yes. Do y'all see this or not? Okay. This is smaller than pi over 2, always. So it's definitely smaller than pi.
So we can always change the numerator to make
Well, yeah,
make it work. To any constant that we want.
as long as this is bounded, though. See, if this had just been n, I couldn't pick pi, because n grows as n, you know what I'm saying? As n gets bigger, that gets bigger. You could do n plus 1, but then you have to know what that does over there still. So as long as it's bigger. So the key to this is that I know arctangent n is bounded. So it's never going to get bigger than pi over 2. I could have picked any number bigger than pi over 2 over there. Yes? Okay. Now, that holds, right? That's true, always. This is true for all n, greater than or equal to 1. If you say for all n, I'll be happy, okay? Because I understand that we are agreeing that n starts at 1, n is an integer. So you can say for all n greater than or equal to 1, or you can say for all n, either way. That's true. Have we satisfied what we need then? Therefore, what's going to happen? Which one? Therefore, the sum of the absolute value of arctan n over, oh, I'm sorry, I forgot the negative 1 in there. Yeah, but I'm trying to say that the original series, right? Therefore, that does what? Converges by the comparison test.
So, like, going back, we had instead of arctan on top just n over n squared,
Mm-hmm.
the denominator, right?
Mm-hmm.
We can make up a b sub n with just b greater, just with n.
But you need to know what that b sub n does. You would have to know what it does. You would have to know if it converged or diverged. And that's why it gets complicated, because you might be able to find something that, yes, it's going to be bigger, but do you know what that does? So that's the trouble. Now, we're not done here, right? But I've only shown that the absolute value of that series converges. That's right. I need to state that, though, okay? And then using theorem 8.4, which is what we had in class, which said if the sum of the absolute value of this sequence converges, you don't need to state this, but if you just say using theorem 8.4, I'll be happy. Pardon me? Yes. Yes. You need to explain what you're doing. Because if you make a mistake, if it's not, I'm going to count it wrong. You have to understand your own logic, and you need to be able to put it down on paper. Because the danger is that you start doing things that aren't legal. You start doing, like, how could I say it? Let me finish this, and I'll give you an example. Using theorem 8.4, therefore, sum negative 1 to n, or negative 1 to the n arctangent n over n squared converges.
Can I just say,
Yes.
right after you have the absolute value, right?
Mm-hmm.
Put a comma, then just put then the original one converges, because that's how it is here over here.
Why does this converge? Why? This statement right here, I'm saying this converges. Okay, so I'm saying that. I'm saying I did that by the comparison test. And because that converges, it forces the original one to converge. Why are y'all trying to not write? Write your work. I mean, this is part of what it takes to be a mathematician, engineer. Write your work. Make it make sense. We're not going to run out of paper, right? I mean, it really is about expressing your ideas on paper so that other people can make sense out of it, not just you. I mean, because you may pull this out in 3 months and you may have no idea what you're doing. If you can write it down in steps and understand it, It's better. It's better. And you have to convince me. Okay? Because just because you get an answer that says it converges and that's correct, that doesn't mean you're going to get it right. You have to logically explain what you're doing. So here's a danger, right? You take something like this. Take the absolute value of it. Same thing as that, right? What is that? Harmonic. So what then? Diverges? Therefore what? The original one diverges? No. No, that'd be wrong. Because if the absolute value converges, that converges. But if that diverges, that doesn't tell you anything. You would have to use alternating series test on that. Alternating series test would show you that that converges, this one diverges. So you don't want to just be getting to this thing where it's just like, okay, I do the test, whatever the result of that test is the answer to what I'm looking at. You have to understand everything in it. Am I making sense? You have to understand how each piece is connected, because you may get a result that is wrong. So the more you put down on paper, the more I see that you understand. All right. What's that? We did that already. I did that in class. Yeah. You do alternating series on that right there. All right. Well, what do y'all think of this? So, I mean, how are you starting to feel with this whole idea of series and tests? And do you think you're gonna be ready on Thursday? I will tell you, the only series I'm going to prompt you on would be telescopic. When it comes to a collapsing or telescopic series, I will say, find the sum of this telescopic or collapsing series. So you know that it's the type where you have to write them all out and find the pattern and cancel and get everything to collapse. I'll let you know. Other than that, everything else is just, here it is. Either determine convergence or divergence or find the sum. Yes? It's looking like 8.4. I don't think I'll do much. Maybe if I talk about 8.5 today, it'll be a bonus on the test. I have no idea how many questions. Yeah. This will be chapter 8. 8.1 through 8.4. Yep. Now, there's not going to be a whole lot from section 1. We'll talk about the test at the end. I've already got the problems that I think you should look at, and I've got it all written down. But let's finish up what we didn't last time, and that's the ratio test. Or not the ratio test, the root test. This is our last test. And the root test, again, says given a series, any series, all right? So it can be alternating, doesn't have to be positive terms only. It says that if the limit as n goes to infinity of the nth root of the absolute value of a sub n equals some number L, and it can be positive, all right? I mean positive. It can be infinity, so it doesn't have to be a finite number. So if that limit is some L, then the series converges if L is less than 1, and the series diverges if L is greater than 1 or infinity. And what if L is 1? Inconclusive. So if L is, and now it says it on your sheet here too. On the right side of root test, inconclusive. Also says here on your sheet, it's useful if a sub n involves nth powers. Geometry. You ready to do one? Okay. All right, first example is sum n equals 1 to infinity n squared over 2 to the n. That's almost the same as the problem that I gave you for your quiz just now, isn't it? Except I had n to the fourth and I had 7 to the n. So we know we could do this with ratio test. It could work. But let's see how the nth root test, root test works here. So for us, what's a sub n? That thing right there? What is the limit as n goes to infinity of the nth root of the absolute value of a sub n? That would be limit n goes to infinity of the nth root of n squared over 2 to the n. Oh, yeah, you don't need the absolute value in this problem. Is that okay? Now, remember from at some point in your life what it meant to take the nth root of something. That was the same as taking it and raising it to what power? 1 over n, right? 1 over n. Right, like square root was same as 1/2. Cube root was same as 1/3 power. So nth root is same as 1 over n. So this is limit n goes to infinity. Now what I'm going to do is I'm going to apply the 1 over n to each, the numerator and denominator separately. So I'm going to go n squared to the 1 over n. And then on the bottom, 2 to the n to the 1 over n. Do you all see what I did there? And when you have something to a power, how do you combine them? How do you do these together? What is it? Multiplication. Multiplication. So I have limit n goes to infinity of, on the top, what would I have? N to what? 2 over n, right? And on the bottom, what do I have? Just 2. 2 to the n over n is 1. Still with me? Well, what happens as n goes to infinity here? You have this right here goes to infinity raised to what? To 0. And this is an indeterminate form from Cal 1. An indeterminate form. Because the base wants to get big, the exponent raising something to the 0 wants to turn it into a 1. We dealt with this way back when we were doing triangles in a circle. Is one of your take-home problems, right? Indeterminate forms that look something like this. So what I'm going to do here is on this scratch work, really, I'm going to do the limit as n goes to infinity of just that piece, n to the 2 over n. Anyone remember how to do this? Yeah, you're going to do natural log. So what we did is we called this y. And then we did natural log on both sides. And I said that the natural log can pass through the limit. And that the power on the end would drop in front of the natural log. I hope that if you're still uncomfortable with this type of indeterminate form that you get help on it. You know, come to me. Natural log both sides, power drops in front. And now you can rewrite this right side. You're probably thinking ratio test might have been better, huh? 2 natural log n over n. What I'm doing is I'm taking the 2 over n in front. I'm putting the n on the bottom instead. Because that goes where as n goes to infinity? So, natural log of n on top goes where? Infinity over infinity. So you have infinity over infinity. Now you can apply L'Hopital's rule. Natural log y through L'Hopital's rule equals limit n goes to infinity Derivative of top is 2 over n. Derivative of bottom, 1. Now let n go to infinity. You get 0. Now you need to get back, what's y? E on both sides, right? E to natural log y equals e to the 0. So y is what? 1. What's that? Indeterminate forms, Cal 1. So, I mean, look, here's what I'd say. If you don't understand what's going on here, just start and come talk to me. We can work through that. But that, at this point, is just something we should be able to do on the side. Okay, so what is the answer here? The top here goes to 1/2, right? And the bottom is 2, which is 1/4, which means it's less than 1, which means what? Therefore, the original series, forgot what it was, n squared over 2 to the n, converges by the root test. Yes. Yes, we could right here. Oh, whoa. Right here, take the limit in here and do that first. You could. Mm-hmm. Well, the limit can go in the root, but then, okay, so what would that be? Okay, so you would get 0. And then you have 0 to the 1 over infinity. Because you'd still have the n on the outside, the 1 over n. Yeah. The n is affecting, see, the n is affecting the root, and look, if this was just like 5th root, we could pass the limit inside. But see, the root is affected by the n also. It's like you can pass a limit through a cosine, or you can pass a limit into square root, but the root here is dependent on the n also. The limit is affecting both of them. So even if you were to go in here and figure out what's going on here, you still have to eventually let that n go to infinity. So you wouldn't be able to avoid it because the inside here would still go to 0, but then you'd have 1 over n. And you'd have to let n go to infinity, so you have 0 to the infinity. Or 0 to the 0, sorry, 0 to the 0, which would be indeterminate again. So you'd be kind of stuck. Yeah. Was there another question? Yes. Well, this isn't a good example. This just shows you the problem we did before can be done this way. Right? What's that? Where? N to the 2. Y is 1. Oh yeah, the whole thing is 1/2. Where did we get this y? I'm glad you pointed out. This y right here. Hold on a second. Hold on. Is this right here, right? Okay, that right there is y. So this should be a 1 there. Let's fix this, okay? It doesn't change our result, but it should be. I think I had done 1/2 in my head, and then I plugged it in again, and I don't know. Brain fart. Okay, so to answer the question, though, this was just to illustrate that you could do the example that we've done a different way. I would never have done it this way, though. So let me give you another example that wouldn't be, well, The next one, let's see the difference, and we'll see which one would have been better. How about 2 to the n over n cubed? Look at this one. Yep, our a sub n's here. Let's try root test on this. I mean, I see we could maybe try comparison with a p series, right? P being 3, maybe that would work. Or what? Or ratio. Ratio might work here. But let's just illustrate how the root test works. So I want to take the limit as n goes to infinity of not square root, nth root of 2 to the n over n cubed. And watch this. This is limit n goes to infinity of, what does the top turn into? If I split these into 2, that's just a 2 on top, the nth root of 2 to the n. On the bottom, it's n to the 3 over n, right? Indeterminate. But we could do that pretty much the same way we did the last one, right? So I'll move much quicker through that. So when I do natural log y on both sides, that 3 over n is going to come out, and I'm going to drop the n on the bottom already. So since we just did one just like this, except it was n to the 2 over n, exactly the same except with the 3. If we do this now L'Hopital one time, three over n over 1, we get 0 again, which means that y is 1. So the answer here is what? Going back up here, it's 2 over 1, which is greater than 1, which means the original series diverges. So therefore, sum 2 to the n over n cubed diverges by root test. That one was pretty much like the reciprocal of the previous one. So, good? Yes. Nth term. Absolutely. But you would have had to do a couple of L'Hopitals, but it would have worked. Yes. Everyone see that? Nth term test would have worked here? Because if you just, that was the first test we ever got, right? Let n go to infinity on this right here, on that. You get infinity over infinity, take the derivative one time, right? Then second time, by third time, the bottom is a constant, the top just keeps growing, so yeah. But I'm just, again, trying to illustrate the root test and how it can be applied. Now let me give you an example of one that you won't be able to use another test on. The what? This right here? That? Why that's true? Derivative of natural log of n is 1 over n, right? So 3 times 1 over n is 3 over n. And then derivative of n is 1. And then let n go to infinity. That all right? Okay. All right, last one for root tests. How about sum n equals 1 to infinity, 1 over 1 plus n to the n? Now, there's a lot of things you might try on this, but it's difficult to see what's going to happen here. Like comparison, what are you going to compare it to? That power n really changes the game. That nth power out there changes a lot of things. So you could try ratio, okay? But let's just see how clean the root test would be here. If we let a sub n be this, then the limit as n goes to infinity of the nth root of the absolute value of that, which is just this, the nth root and the n cancel each other, right? And you're just left with limit n goes to infinity of 1 over 1 plus n, which is what? 0, which is less than 1. Therefore, it converges. Okay? Now that's an example where this test is perfectly suited for. You wouldn't want to use another test because this one just comes out really clean.
So like there's I think there's two tests that we can use most of the time working. The ratio test and the root test.
Ratio is a really big test. The ratio test is one of the biggest tests. It works a lot of time. I mean, not works works a lot, but it also depends on what the problems you're presented with. It's 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 shown more. Okay, a lot of textbooks show more examples of ratio tests because of where we're going. Where we're headed requires lots of ratio tests. Nope, unfortunately. Just like integration, there's not going to be a universal, here's the fix, you know, here's the pill, the magic pill. Yeah, no, it's not like in Cal 1 where you do the derivative and they do the limit the whole time, and then at the end they say, oh, no, here are the rules. Here are the shortcuts. It's not going to be like that. N equals 1 to infinity. I want to look at that same problem we just did because I want to see it with the ratio test. Okay? I just want to to show you like at what point you would say, maybe not. Okay? If you do ratio on this, you're doing limit n goes to infinity of a sub n plus 1. 1 over 1 plus n plus 1 to the n plus 1 over the other, just a sub n, which is 1 over 1 plus n to the n. Well, limit, hold on. So what you have here is 1 over 2 plus n to the n, and then you could try peeling off that 1, but then over 1 plus n to the n. And you don't get cancellation because they're not the same, right? They're different here and here. And so, no way. All right. I don't want to do it either. So this is a series, all right? It's a sum of an infinite number of terms, and we need to find a formula for it so that we can somehow do a test. So do you see a pattern? Yeah, but if I keep going, they keep tacking on more every time I go, right? The numerator increases by 4. Each factor goes up by 4, and then on the bottom, each factor goes up by 3. So it's kind of like multiples of 4, multiples of 3, but we're not adding them together. So I'm going to help you on this one. Do you agree that this is the same as sum n equals, let me start it at 1 to infinity, of 2 times dot, 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 all the way out to the, watch this, 4n minus 2. Let's see if that makes any sense at all. That's my top. Does that make sense or not? If I let n be 1, where would I go? What would happen on top? N is 1, I go 2 times n times. N is 1, that's a 4 minus 2. It's 4 minus 2. 2. So I go 2 times all the way out to 2. But that means I'm at 2, right? Just stop at 2. This dot, dot, dot means keep multiplying until you get out to there and stop. So I'm going to go from 2 and stop when I'm at 2, but I'm at 2, so that would give me the first one up here. Okay, let's try. Plug in 2. Let me see. Plug in 2, what would happen? 4 times 2, 8, minus 2 is 6. So I'm going to go 2 times 6. Now go out to 3. What would I get on the third term? I get 2 times, now at 3 it's what? 4 times 3 is 12, minus 2 is 10. So I go 2 times, what was the one before? 6, then times 10. Do y'all kind of see that? These are tricky. That's why I'm kind of giving them to you right now. Say again? Well, it's not 2 times 2. This is where you stop. But if you're at 1, you are actually at 2. So you stop as soon as you get to that, but that's the first one. This basically says you're going to be multiplying multiples of, not multiples of 4, but like you're going to start out at 2 and then keep increasing by 4 on each one. And you stop when you get to wherever you are here. So if you're at like 5, 4 times 5 is 20, minus 2 is 18. So you would go 2, increase it by 4, 6, increase it by 4, 10, increase it by 4, 14, increase it by 4, stop at 18. Nay or nay? That's your stopping point. No. It's this starting point, but it's telling you where to stop here. This is, when I say times and then dot, dot, dot here, I'm saying there's a pattern, okay? But that pattern needs to stop, so I want it to stop somewhere. I want it to stop when you get to, well, wherever you are here. Look, start over. Let's look at this one right here. How do I tell you I want you to do 2 times 6? If n is 2, it should give me this term right here. Okay? So if n is 2, I'm going to stop, let's see, 4 times 2 is 8, minus 2 is what? 6. So I'm going to go 2, increase by 4, 6, and that's where I stop. If it's 3, then what would it be here? 12 minus 2 would be 10. So I'm going to start at 2, and then I go to 4 more than 2 is 6, and then 4 more than 2 is 10. That's where I stop at 10. That's right. See, the 4n means you're going to increase by 4 every time you go.
But right before that, you have to add 4 to the 2, right?
Yes. Kind of, but not because it's not 2 times 3 times 4. If you had a factorial up there, then that would work. I mean, that's if it was a factorial, then it would just be factorial and factorial. That's all we would say. What about the bottom? What's the pattern on the bottom? They go up by 3 every time. And where does it start? 5. Okay, so it'd be 5 times ... dot 3n, then what? Plus 2, because that'll start you at 5. With n is 1, it'll start you at 5. What do y'all think? It's weird, huh? Uh-huh. That's where I'm starting, yeah. So now if n is 1, we're basically going to have 2 over 5, right? If n is 2, then it's 2 times 6 over 5 times 8. If n is 3, then it's 2 times 6 times 10 over 5 times 8 times 11. The ... means that there's a pattern. That pattern is established by this. If it's what? If it was 1 where? If we're supposed to stop at 1? Yes. Yeah. Only for 1, though. Only for n is 1. After that, they start picking up factors. Okay. Does it converge or diverge? We're going to do ratio test. A sub n is equal to 2 times ... times 4n minus 2 over... See, we've never had one of these before, had we? Times 3n plus 2. Never had a series that looked like this. What would a sub n plus 1 be? It'd be 2 times ... till I get out to what? 4 parentheses n plus 1 minus 2 over 5 times ... 3 times n plus 1 plus 2. Before I go and I do ratio tests, let me clean these up. 2 times ... 4n, what is it? Plus 2, all over 5 times ... 3n plus 5. Yes.
Can I just from the beginning guess that it will converge? Not guess, but assume that it will converge because, like when it said the cup, right? The denominator is getting bigger past than the numerator. So if they're adding,
How do you know that?
can it go up? Go up. You're adding more, right? But you're adding half and half, a lesser number. Okay. Can I just say that it will converge?
Say it again. Your logic.
When you said like the example of the cup, right?
Mm-hmm.
You're pouring water, like you put a half, then you put like
Yeah, yeah.
whatever. It's happening right there. It's decreasing. You're adding, but smaller numbers. So never.
Yeah, but so is a harmonic series. Harmonic series, same idea. You're adding smaller numbers, right? If you take 1/2 plus 1/3 plus 1/4 plus 1/5, those are getting smaller. But that doesn't mean it converges. Yeah, the tops are getting bigger.
But the numerator, the denominator is getting bigger faster.
How? Convinced? I'm not convinced of that. Well, I'm not convinced of that. Yeah. Look, these are going up every time on the bottom. They're going up by 3. 3. But those are going up by 4. That just moves it. That just moves where it is. So instead of being 10, it's 4. Look, here's the thing. You're not going to be. You've got it. That's why we have the test, because we can't just look at it and say, I think that's what it's doing, because you're going to have an equal number of people say, no, I disagree. So we need a way of, let's resolve it. Let's do it with a test. Okay? Yeah, on a test, you don't want to just say, oh, it's obvious to me that this is converging, right? Because yeah, I need justification on that, please. All right, here comes ratio test. I'm taking the a sub n plus 1, which is 2 times ... 4n plus 2 over 5 times ... 3n plus 5, and I'm dividing it by the other one, right? Which is same as multiplication of the reciprocal. The other one is going to be 5 times ... 3n plus 2 over 2 times ... 4n minus 2. We're almost there. There's a lot of stuff that cancels, aren't there? Yeah. What we need to talk about here is this one right here. Isn't that one bigger than this one? I mean, it's got more there. What's the guy right in front there? What's the guy right in front of this one? It's whatever you get when you go 4 back from here, right? Remember, every one of those was 4. Every time you went out was 4 more. So isn't it just take 4 away? What happens if you subtract 4 from this? What do you get? You get 4n minus 2, right? So what I want you to see here is that this top one, 2 times ... times, it's 4n minus 2, and then the one right after that is 4n plus 2. Do you see that? That's the one right before. The one right before this is going to cancel with the one down there. See it or not? Same thing on the bottom, right? What's the one right before right here? What's that one? It's 3 less than that, so 3n plus 2, and then we still have the 3n plus 5. A bunch of junk goes away here. Everything here and everything here. 2, and then the next one, all the way till that, all the way to the 4n minus 2. And then on the top, it's what? Everything here with everything here. Kind of. It's factors, though. It's not sums. Same idea of, yeah, that you have to go one term back to see it. All right, so what's the only thing left after all that stuff goes away? 4n plus 2 on top and 3n plus 5. Now let n go to infinity. 4/3, which is ratio test greater than 1, which means diverges, sorry. It didn't converge.
Well, I mean, what I was going to say earlier is that if you look at the sequence at the top, it doesn't go to 0, it goes to the number. So couldn't you see from there that divergence?
Wait, hold on. When you go up here,
All the way up?
all the way up, all the way up, Yes.
that it doesn't converge to 0.
Why? Like the Nth Term Test?
Yeah.
Nth Term Test, you'd be trying to look at this and let n go to infinity on it?
Well, okay. The sequence right there.
Yes.
We can. It's already higher than 1. So when it converts to a number.
Where is it higher than 1?
Yeah, that would be.
That's less than 1, that's less than 1, that's less than 1, that is 1.
Yeah. I
So
was looking at that and seeing that it's going to be greater than 1. And that's when it converts to a number.
it's hard to say that. The next one would be what? Top would be 18, the bottom would be 17. Then the next one would be 22 and then 20. So those look like they're going. But see, it's not a clean limit like you do L'Hopital, because you don't have, if you just had this right here, you'd be done. The real heart of this problem, there's a couple things. Can a person convert a series into its summation notation? And then can you mess with ratio test on that? So yeah, no, it's a good conjecture. But see, that one I think is a little more solid, because I see that pattern. I see that the numerators are getting bigger than denominators. Yes, I do see that. But I would have to test it to be convinced. Yeah. All right, well, wow, we only have 20 minutes, less than 20 minutes left. Shall we discuss the exam? It's going to be on Thursday. So what I had looked at was on page 498. 498. This is the chapter review. And let me grab my sheet that has the problems that I liked here. I thought that 1 through 19, all, talk about, what can I study, what problems can I do, and focusing really more on 9 through 19, okay, more than the first 8 problems. First 8 problems involve sequences, which I think you can kind of agree at this point. If you don't understand the sequence, then you're going to have all sorts of hell with the series, right? So there's not a whole lot of sense testing you on series now, sequences, because you kind of need that for series. So 9 through 19 are good. 21 through 27. I will point out that 25 through 27, it says find sum. When someone gives you a series that says find sum, what does that mean? It means it converges. Okay, that means it's probably geometric or it's telescopic. Right? If I tell you to find the sum, that means it has to add up to something, and you have to find out what it is. There's really only a few things we can actually find the sum of: geometric and telescopic. So just keep that in mind. Also, on numbers 21 through 24, it talks about conditional convergence. Don't worry about it. I'm not going to ask you about conditional convergence. I'm just going to talk about, does it converge or not? All right. We can focus on that a little more later on. Now, I wanted to kind of offer you how you could do these, but I don't think I want to give that to you right away. Like, okay, number 9 is this test. Number 10 is this test. I think that'll be your trouble. But when you want that, I can. You want me to provide that at some point? Answers? Answers? Yeah. I can post the answers, and then you can look for them if you want. Okay. Yeah. Does that seem reasonable? I mean, you'll have to go through these and work them out, but there's no crazy surprises or anything. Well, there's a few in there to skip. Yeah, like number 20 is, I would recommend you don't worry about 20 right now. Yeah. 20 is a bit of a pain. And then there's some others that you just don't even want to touch yet, because again, this is a chapter review, so there's some things that they already knew, like picked up in later sections that they're using that we can't use. All right. Is that enough of a review? All right, let's talk about bonus for the test. Yeah, that's a different bonus, though. That's a different one. The bonus for the test will be a question on the test, which will count for bonus on the test. All right. Cheat sheet, what can you have on the test? You can have your review of, you can have that all that other stuff that we had on the other test with all the integral formulas and all that stuff, but you probably won't need it. Maybe you might have to do an integral test. So you might need an antiderivative or something, so make sure you have that.
If we do an integral test, we put like a hard integral, because some of them, like integral test, there's a lot of integration that we can skip.
Will I put a hard one? Are you requesting a hard one? Is that what you're saying? Will you? I'll put one on there, a hard one for you. That's no problem. No problem. I'll do it. I'll do it. That's, you know. I know. I don't know. You know, there's certain, I want to see a demonstration of each of the tests, right? I'd want to see that you can do each of these tests. So, but I can't guide you and tell you, and we know that some tests, some series you can do with multiple tests. So for the integral test, I'm going to have to be very specific to pick something that you can't do with any other test, force you down the integral test road. So I think when you get to that problem, you're going to need to see that it looks like an integral, like something in its derivative is there. Yeah. So I don't think it'll be that bad. Logs and exponentials. I don't even remember what you're talking about. What do you mean? On what test? Oh, if it happened today, it's fair game. Yeah. Yeah. Well, yeah, because that infinity to 0, that's an indeterminate form, so that's expected. Yeah, but I would have done ratio on that one. Absolutely, would have never done the other one. Okay, so let me show you kind of where we're going with this. Okay, because it's hard at this point to understand where this all leads to. If I take a function like, 1, everyone know what 1 looks like? Just flat line, right? Okay, if I graph it. If I say, how about 1 plus x, what's that? A line, right? Flat line that's got a slope 1, it's been moved up 1, right? If I do this, 1 plus x squared, now we've got a parabola, right? Opens up. Now if I do, 1 plus x squared plus x cubed, now I have a cubic function. Actually goes down on the left, up on the right. These are all polynomial functions, right? Polynomials. Imagine a polynomial function that went forever, never stopped. And perhaps the numbers in front of each of them changed. They were different. So the blue circles there, look at those as a sequence of numbers, right? The blue is a sequence of numbers. And everything else is just the power of x. You got this right here, the power in x is 0. Here the power is 1, then the power is 2, then the power is 3. So imagine you've got this infinite polynomial, and the only thing that changes are the numbers in front. You with me? Now sometimes you can have that number be a 0, which kills it off completely, and you still have this infinite polynomial, right? That's called a power series. And here's the unbelievably beautiful part of power series. I'll show you it with a picture. I think the first time I ever understood this tripped me out, all right? Okay. Let me try and fit this all on the screen. Going the wrong way. That's your good old standard sine function, right? Sine function. Now you see that 0 right there? That's my polynomial. So what I have is in red is a sine function, as we all have learned it in our lives. The black is my polynomial 0 by itself. Okay, so it only has one term, 0. Now what I'm going to do is I'm going to add one more term to that polynomial. The term I'm going to add is now I have 0 plus x. Okay? So that means I had 0 plus x. So I have a 0 and then a 1 in front of that, right? Now look at this. Does that line look like it's about sine? Like, would you say that x and sine x are pretty close to each other? Hell no, not even close, right? I mean, maybe towards the middle they are, right? Towards the origin, but after that, man, things are just totally different story. Okay, I'm going to go out to the next term is 0x squared. Okay, it's not there. Now I'm going to go out one more. It's negative 1/6 x cubed. Negative 1/6 x cubed. Now don't ask me about where this came from yet, okay? We're not there yet. I just want you to see what's happening. Look at that cubic polynomial. Does that approximate the sine? Better, right? Better. Now I left the dotted one, the old one there. You see it? I left it there. I left it there just to remind you how crappy our first one was and how much better this one is. Now what if I go again? Okay, I left the other one here. Here's our old one right there, right? Now look at this is a 5th degree polynomial. Look at the coefficient on it. 1 over 120. See it? Look at how good this one is. Isn't this black one here better than that one? You look at it, follows it pretty close. Our other one took off right here, but this one sticks with it a little bit longer, right? And then it starts to kind of freak out, and it doesn't work. Well, if I keep going and going and going and going and going, I basically, I what? Oh, I did. Oops. He keeps moving on me. Well, they're off the screen anyway. But you see the polynomial? You see how good this is? You see how good this is? Now outside, okay, outside it starts to kind of freak out. But somewhere in here, right, it's pretty darn good. So if I was trying to find maybe sine of 2, right? I could either plug in sine 2 on my calculator, or I could plug 2 into this polynomial, and it would give me the same answer. Yeah? Well, that's what your calculator is doing. Your calculator is doing the series. Your calculator has no idea what sine is. Your calculator thinks sine is that power series. Are y'all kind of following that? Every continuous function, this is called the Weierstrass theorem, huge theorem in analysis, okay, is every continuous function, okay, nice smooth function on a closed interval can be approximated with a power series to any degree of tolerance, to any tolerance you want. You can get as close as you want. So give me anything you can draw basically without picking up your pencil, and I can find a polynomial that'll fit it. How good? As good as you want. You want me to be within 1/1,000,000th of the true value? I'll be within 1/1,000,000th. You want me to be within a trillion trillionth to the trillionth power? I can do it. The Weierstrass theorem says it's possible. So that means all in engineering and math and engineering and physics and all that, when scientists are dealing with continuous functions, we know we can always turn them into polynomial functions. And what's great about polynomial functions? They're easy to integrate and they're easy to differentiate, right? If I give you a bunch of powers of x and I say take the derivative, there it is, right? If I say integrate, there it is. Now, you can't get the exact answer because it's an infinite series, but the further you go, the more accurate. Does that make any sense? All we've been dealing with so far, all we've been talking about are the coefficients. That's it. That's what we've been dealing with, the numbers in front, and figuring out if they converge or diverge, right? If you add them up, will it converge or diverge? So for this, it turns out for sine, I can keep going in this power series, keep going and going, and I will fit that sucker right on top of sine. If you let me go and get like a million terms, it'll be really good. The more terms I go, the better it is. That's sine. Here's another function. 1/1 minus x. Here's my approximation. You see it? That one right there? That line right there? Kind of sucks. Go a little further. That's better, 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 better. There seems to be something kind of weird happening here. Even though I keep going out, it seems like once I get past a certain number, I can't get this series to keep doing what this one's doing. I can't get it to happen. Well, that's because outside a certain window, my power series doesn't converge. All right? So you know how we said converge and diverge? It turns out that once we throw x's in here, those x's are going to somehow determine also if we converge or diverge. So this is like saying, okay, as long as our x's are between 1 and -1, I can put a power series on top of that, and I can estimate it. But as soon as you go outside that, it doesn't converge. And so that's why convergence and divergence has been so important to us. It gives us some sort of idea of when we can and when we cannot approximate this. Well, that we'll call the radius of convergence later. All the functions, all these functions that we've known our whole lives. Here's e to the x, our wonderful exponential function. I start throwing my power series on top of that. It turns out with e to the x, I can match up e to the x. There's no like radius of convergence. I can always go out further and get closer and closer. Here's another one, e to the -x squared. I put this example in here because e to the -x squared is an example of a function that cannot be integrated. There's no technique of integration. There's no way to integrate that function. However, because of power series, we can fit a power function on top of it, and we can go as much as we need to go. and get as accurate as we want to go. Now we may have to go pretty far. A lot of terms we can put power function on top of it, and that means we can integrate. If we want to integrate e to the negative x squared, what you do is you integrate each of these. And then when do you want me to stop? Well, how tight do your tolerances need to be, right? You building a table, or you building a wafer that has to have a bunch of microprocessors on it? I mean, the tolerances on something like that are more than like where you can put the holes on this table so you can put the legs in. You know what I'm saying? Like, we don't care too much there. That's what the power series gives us, an ability to control how accurate we need to be. I hope all this makes sense. We're headed this way. What it's going to eventually turn out to be for us is I'm going to give you a function, and I'm going to say, we'll call it a Taylor series. We'll find its Taylor series expansion. So turn this function that you've known your whole life into a power series. All right, I'm dying up here. I don't know what's happening, but even if I die, we'll still have the test on Thursday. I'll get it to someone. Y'all have a good day. Between now and Thursday, I'm available for help if you need it. I don't know. Oh, what's the bonus? I don't know. I covered it. So, I mean, I'm not going to ask you to create a power series, but I might ask you a question about it. Yeah.